Hello and welcome. Today we're going to go on a pretty magical journey, chalk in hand, to sketch out one of the most incredible stories in all of science, the story of the atom. So let's join in and see how this amazing picture came to be. So, meet our guides for this adventure, Kiki and her brother Suso. They're about to tackle a question that has puzzled people for, well, thousands of years. If you could just keep cutting something in half, over and over, would you ever get to a point where you just couldn't cut it anymore? You know, that exact thought actually occurred to philosophers way back in ancient Greece. They imagined this final, fundamental particle, and they called it atomos, which literally means not to be cut. It was a really beautiful idea, but for 2,000 years, that's pretty much all it was, just an idea.
And then things started moving, and I mean fast. In just over a century, our whole picture of the atom would be drawn, erased, and then completely redrawn. So let's follow along as Suso starts sketching out the discoveries of these key figures.
Okay, first up is John Dalton, back in 1803. Suso draws a simple, solid circle on the board. See, for Dalton, atoms were like these tiny, indestructible billiard balls. All carbon atoms were identical little balls, all oxygen atoms were identical, and they just combined in simple ways. This was the first truly scientific model of the atom.
But Kiki, who's always curious, she's got a question. She's like, okay, that's a nice little ball, but what about sparks? You know, when you rub a balloon on your hair, where does that static electricity come from? Dalton's model? It had no answer. The atom needed more detail. And then the first big clue dropped in 1897. A scientist named J.J. Thomson discovered the electron, a tiny, negatively charged particle. And now this was a huge deal. It meant that the 2,000-year-old idea of an uncuttable atom was just wrong. For the very first time, we knew the atom had smaller, more mysterious pieces inside. Dalton's simple little billiard ball was officially shattered.
So Suso erases that solid circle, and now he draws Thomson's new idea from 1904. To account for those negative electrons, Thomson pictured the atom as this sphere of positive pudding with the tiny electrons scattered all through it, kind of like raisins. This became the famous plum pudding model. Now, what's really interesting about this next part is that the scientist involved, Ernest Rutherford, he fully expected to prove that the plum pudding model was right. He set up this experiment that he thought would be totally straightforward, but instead it led to one of the biggest shocks in the history of physics. So here was Rutherford's plan. He was going to fire these tiny positive particles, they're called alpha particles, at a super thin sheet of gold foil. Now, according to the plum pudding model, that positive charge in the gold atoms was all spread out and kind of soft, so the alpha particles should have just flown straight through like bullets through well pudding.
But that is not what happened. Not even close. Yeah, most of the particles sailed right through, but about 1 in every 8,000 of them bounced back, deflected at these sharp angles like they'd hit a solid wall. Rutherford was absolutely stunned.
And this quote just brilliantly illustrates his surprise. I mean, listen to what Rutherford himself said. It perfectly captures the moment. The only way those particles could possibly bounce back is if they were hitting something incredibly small, super dense, and positively charged.
So Suso erases the pudding model, and in its place, he draws Rutherford's completely radical new idea from 1911, the atom is mostly empty space. All the positive charge and almost all the mass is packed into this impossibly tiny center, the nucleus, with electrons orbiting it like little planets around a sun.
But Kiki, she spots a problem with this new drawing. She asks, wait a minute, if the nucleus is positive and the electrons are negative, opposites attract, right? So why don't the electrons just spiral into the nucleus and everything goes poof?
And you know what? She was totally right. According to the physics of the time, that is exactly what should have happened. Rutherford's planetary model was unstable. There had to be some other rule, some kind of magic almost, that was holding the whole thing together. And this puzzle set the stage for Niels Bohr.
Bohr, a Danish physicist, he took this bold leap in 1913. He basically proposed that the atomic world plays by a completely different set of rules, quantum rules. Think of it kind of like a ladder. Electrons can't just stand anywhere they want. They're stuck on specific rungs or energy levels, and they can't exist in the space in between.
So Suso draws this new model on the board, showing these crisp, clear orbits. And here's the really cool part. When an electron jumps down from a higher shell to a lower one, it releases a little spark of light. This model perfectly explained the specific colors of light that hydrogen atoms give off. It was a huge success.
But science never stops asking questions, and it turned out Bohr's model was, well, a little too neat. A strange new rule of quantum physics called the Heisenberg uncertainty principle revealed there's a fundamental limit to what we can even know. The more you know exactly where an electron is, the less you can know about where it's going, and vice versa. So a perfect, predictable orbit? Simply impossible. Bohr's neat little circles had to be smudged.
This brings us to our final pioneer, Erwin Schrödinger. In 1926, he took all that uncertainty and built a whole new picture around it. He suggested something truly mind-bending. What if the electron isn't really a tiny thing at all? What if it's more like a wave, a spread-out ripple of possibility?
And hey, even Niels Bohr admitted how strange all this was. His own quote is the perfect way to get ready for the final picture of the atom. It's not intuitive, it's not simple, but it is the truest description we have of reality.
And with a final, gentle smudge of the chalk, Suso erases those neat orbits. He draws the modern view, a tiny nucleus surrounded by a beautiful, hazy cloud. Now, this isn't a picture of the electron itself. It's a map of where the electron is most likely to be found. The atom isn't a tiny solar system, it's a cloud of pure potential.
So just look at that journey for a second. We went from Dalton's hard, simple little ball, to Thomson's pudding, to Rutherford's mostly empty space, to Bohr's neat orbits, and finally, to Schrödinger's mysterious, beautiful cloud of pure potential. Every single step was a leap of imagination, all driven by evidence.
The story of the atom really shows us that science is never finished. Kiki and Suso look at their final drawing, and it's a testament to a whole century of genius. It really leaves us with a fascinating question. If our understanding changed this much in the last 100 years, what new, magical picture will we be drawing in the next 100?